All right, we're looking at FRQ number 3 of the AP Calculus AB free response questions. If there are any corrections, I will put as a pinned comment in the first comments in the video. So the depth of the seawater at location can be modeled by function h that satisfies the differential equation. It is known that h of 0 equals 4. A portion of the slope field is provided. Sketch the solution curve through the point 0, 4. So here's the curve, and then you're just going to kind of follow that curve around like that. Okay, so just kind of connecting the dots like that, or connecting the hash marks. It can be shown that h of t is greater than 1 for the value of t between 0 and 5, at which h has a critical point. Determine whether the critical point corresponds to a relative min or relative max, or neither a relative min or max at the depth of the seawater at this location. So they're finding a value of t which has a critical point. So critical point, first thing you got to identify is that's where h of t is definitely equal to 0. So when does that occur? We have a derivative, and we want to know when that occurs. That's 1/2 h minus 1 cosine of t over 2 is equal to 0. That's what that derivative, because this is the derivative, right? They're telling you h of 1, so when I have a bunch of things, either this is 0 or this is 0, but because h of t is greater than 1, this cannot be 0. So that means the only way that this product can be 0 is if cosine of t over 2 is equal to 0. And that is where and that's where is cosine 0 on our unit circle. Cosine is 0 at pi over 2, 3 pi over 2, and stuff like that. Pi over 2, 3 pi over 2. 3 pi over 2 is like 10 over 2. This is like 9 over 2, 4.5. And then when you times 2, that means t is equal to pi or 3 pi. 3 pi is definitely past 5. So it's definitely just pi is the location. T is equal to pi is the location. And then they're asking you whether it's a relative min or max. Now, the easiest way to do this is when you have okay, there's a couple ways you can I guess do this. You could look at this curve and say that, like, it's a relative max there, right? Like that's what it looks like, because at pi is 3.14, it's around here. So one thing you could simply do is just say, like, well, from the graph, there's a relative max at that point. For h being greater than 1, because we're above this point, and so you can see that it's a relative max. That's probably not a very common way to do it, but that in this case, I think that would be a valid way to describe it, that it's a relative max. The more standard way we do relative, if that didn't occur to you, the more standard way we do that is we can look at the first derivative test, and we can decide whether or not this thing is positive. So we can make a number line for dh dt. Right? And then we could say, is it going from increasing to decreasing? In our interval, we're only carrying from 0 to 5. And then pi is like right here. Now, the thing is because h is always greater than 1, you know that this thing is always positive. So then it's just a question, is cosine in this interval, is it positive or negative? Cosine of this over 2. Well, if I plug in like pi over 2, cosine of pi over 4 is definitely positive. So this would be positive, and this will be positive. So that's positive. And then from there to there, from pi to 5 pi, or to 5, you could pick like, not 3 pi over 2, but maybe pick like a little bit past here, right? The cosine goes on to, the cosine of divided by 2 will be in this region, so the cosine value will be negative. So this will still be positive, because again, h is greater than 1. So this is positive, times a negative number, that will make it negative. And so this is a relative max. Relative max, because it goes from increasing, because dh dt goes from positive to negative. Okay. Use separation of variables to find y equals h of t, the particular solution to this differential equation. So we're going to start with that initial condition here. So we have dh dt is equal to 1/2 h minus 1 cosine of t over 2. So then we're going to move the h minus 1 dt up and move the h minus 1 over here, because we want to separate all the variables. Goes 1/2 cosine t over 2 dt. And then now we can integrate both sides. This side, you can do a u substitution, or just recognize that the antiderivative is going to be that. This, again, you could do a u substitution, or just recognize it's got to be sine of t over 2. You can do a u substitution with u equals t over 2 if you want. You don't have to, because I know when I take the derivative of this, a 1/2 pops out by chain rule, and that will give me this guy right here. So this would be, and then don't forget your plus c. And then we put e as the base to get rid of the natural log. E to the sine t over 2. And then instead of plus c, we just make it e to the c. And then when I make this e to the c an arbitrary constant c, I can strip away the absolute value. Like that. And now I'm going to add 1, but I also want to figure out h of 0 is equal to 4. So my h, I'm running out of space over here, but I'll just do it over here. So h is going to equal c e to the sine t over 2 plus 1. And then we plug in our initial value here. So we get 4 is equal to c e to the sine of 0. Sine of 0 is 0. Oops, plus 1. 1, that's c plus 1. So that means c is going to equal 3. So that means my h is going to be 3 e to the sine t over 2 plus 1.